everyone, and welcome back. My name is Mr. Cobalt, and in this video, I'm going to go over valence bond theory and how it applies to Lewis dot structures. So let's get into this. So, valence bond theory is basically a theory that's used to describe the formation of covalent bonds in molecular or covalent substances. So it's a very simple model. It's simplified, and it's based on two assumptions. One is only the highest energy electrons, which are the valence electrons, are going to participate in bonding. So no lower level hydrogens are going to participate. So no d electrons are going to be participating in the bonding. Only your s and your p electrons in the highest energy levels of your atom is going to participate in the bonding that forms between them. The second assumption is that covalent bonds are usually formed by pairing up unpaired electrons. So if one atom has one unpaired electron and another atom has an unpaired electron, then the idea is that they're going to form a bond so that those electrons can bond or form a pair, and those that pair of electrons will be shared between the two atoms, forming the covalent bond. And so those are the two assumptions of valence bond theory. So again, one, only the valence electrons are going to be participating in the bonding process or the formation of bonding, and they're going to pair up unpaired electrons. So bonds formed by pairing up unpaired electrons between atoms. So let's go over an example. So what do we mean by the valence electrons? So valence electrons are the electrons in the highest energy level, the outermost energy shell or energy level of your atom. And so here's an orbital diagram of fluorine. So fluorine has 2 electrons in the 1s orbital, has 2 electrons in the 2s orbital, and has 5 electrons in the 2p orbital for a total of 9 electrons. And so we're not interested in the 1s, we're only interested in the electrons that are in the highest energy level. So 2 is the highest energy level, so 2s and 2p. So these are your valence electrons. We're going to ignore these other electrons that are referred to as core electrons. So we don't care about the core electrons, only the valence electrons are going to be involved in your bonding. And you'll notice here that fluorine has 1 unpaired electron, and it's got 3 pairs or 3 lone pairs here when we're looking at the orbital diagram here. So we can represent that as what is called a Lewis dot symbol. And the Lewis dot symbol is where you take the symbol of the element and you put dots around it. The dots represent the valence electrons in the atom. So the number of dots should correspond to the number of valence electrons in your atom. So since fluorine is in group 7 and the group's number in your A groups corresponds to the number of valence electrons in your atom, then you should have 7 valence electrons. So we're going to have 7 dots around our fluorine. So basically, this is what your Lewis symbol looks like. You've got 1 unpaired electron, which matches up with that one there. And then you've got 2 lone pairs, 3 pairs of electrons, 1, 2, and 3. And that corresponds with these 3 here. And so how you write your Lewis dot symbol really depends on you. You should have 3 lone pairs and 1 unpaired electron, but where that unpaired electron and the lone pairs are on your symbol really is up to you. So you could have the unpaired electron on this side with the 3 lone pairs on the other 3 sides, or you could have the unpaired electron on the top with the 3 lone pairs on the other 3 sides, or you could have the unpaired electron on the right, or you could have it on the bottom. Whichever one you choose, it's the same regardless. So how do you get your Lewis dot symbol? So let's go over that really quickly. So you get your Lewis dot symbol by taking the element symbol and putting the number of dots, the dots that correspond to the the valence electrons around your symbol, and you do it in a orderly fashion. So, for example, if we do for hydrogen, if we walk our way through across the periodic table in groups 1A through 8A, let's start with lithium. So lithium is in group 1, so it's going to have one valence electron. So we can put that one valence electron either on the top, the bottom, left, right, right, left. It doesn't matter where you put it. So you could put it here, or you can put it there or there, as long as you have one dot. So there's the dot. Or you could put it on top, it doesn't matter. You could put it there. So as long as you got one dot, this would be the Lewis symbol for lithium, and that would be it. So it has one valence electron, and it's got one dot. So then if we go to the next one, which is beryllium, so Be, beryllium is in group 2, so it has two valence electrons, so it's going to have two dots. How you put the dots is going to be one at a time. You put the dots, you don't do this. Don't pair them up right away. That would be wrong. That's not how you do the Lewis dot symbol. So since we have two valence electrons, we're going to need two dots. We put one dot on each side of the symbol, down, left, or top, right, bottom, left. And we put one electron at each side going around. Now you can go around clockwise, you can go around counterclockwise. It doesn't matter as long as you're adding one electron to each side first before you pair them up. Don't pair them up right away until you're forced to with the number of leftover electrons. And I'll get to that as I'm going across. So beryllium has two valence electrons. It's group 2. So we're going to put a dot on the top and then a dot on the right. So that would be the Lewis symbol for beryllium. And if we go next to boron, boron would be in group 3. So it has 3 valence electrons. So we're going to add 3 dots. So it's going to be 1, 2, 3. Notice I'm going around, adding 1 dot to each side before I pair. So since I only have 3 dots, I can't add any more. So that would be the Lewis dot symbol of boron. And again, these dots can be on any 2 consecutive sides. So this dot could be on the right. These 2 dots could be like this. So I could do dot here, dot on the bottom. Or these 3 could be flipped or turned this way. So I'd have a dot here, dot there, dot there. As long as I am going in a circle around the symbol, it doesn't matter where I start. I could start here and go dot, dot, dot. I could start here and go dot, dot. It doesn't matter as long as you're following the pattern. So as long as you're working your way around, either clockwise or counterclockwise. So next is carbon. So C, carbon. Carbon is in group 4, so it has 4 valence electrons. So I'm going to start on the top again. 1, 2, 3, 4. So that would be the Lewis symbol for carbon. Next would be nitrogen. So here I have 5 valence electrons because it's in group 5. Or it's in group 5 because it has 5 valence electrons. Actually, it's in group 5 because it reacts like the other elements in group 5. So here, I have 5 valence electrons. So I'm going to start on the top again. So I'm going to put 1, 2 on the right, 3 on the bottom, 4 on the left, and then I have 5. Now I start to pair them up. Now I have a lone pair. So I have 3 unpaired electrons and a lone pair for my nitrogen. Next would be oxygen. So oxygen has 6 valence electrons. So again, I'm going to start on the top. I put 1 dot, 1 on the top, 2 on the right, 3 on the bottom, 4 on the left, 5 on top again, pair that up, and 6 on the right again, pair that up. Notice that I'm pairing them up across and down. Like, so I'm not pairing these on the right like this. I don't pair them up like that. And I'm not going to pair this one on the bottom like that if I had another one. That's not how you pair them up. You pair them up as if they're on the sides of a square, right? So this side, they pair up. Down this way, they pair up. So I'm going to pair up like that. Next, after oxygen, we have fluorine. We already have fluorine here. How did I get that? Well, fluorine has 7 valence electrons. If I start on the top again, I go 1 on the top, 1 on the right, 1 on the bottom, 1 on the left, and then I keep going. So that's 4, 5 on the top, 6 on the right, 7 on the bottom. Notice that I'm putting them next to each other this way, so I'm forming a square. And then finally we have neon. Neon has 8 valence electrons. It's in group 8. So again, 1 on the bottom, 2 on the right, 1 on the top, 1 on the top, 2 on the right, 3 on the bottom, 4 on the left, 5 on top again, 6 on the right again, 7 on the bottom again, and 8 on the left again. So there I have my neon. And so that's how you write the Lewis dot symbols for elements in each group. So every element in group 1 is going to have 1 dot in their symbol, just like this. And again, the dot could be anywhere. All elements in group 2 are going to look like this. The only difference is that the symbol is going to be different, right? So if I did sodium in group 1 would look like this, right? And then magnesium in group 2 would look like that. And if I keep going, next I have aluminum. Aluminum is in group 3, so it would look like that. And then I have silicon, Si. So silicon would look like that, and so on. Phosphorus is in the same group as nitrogen. So 1, 2, it has 5 valence electrons. It's in group 5, 3, 4, 5. And then oxygen, sulfur. Sulfur is the same group as oxygen, so that has 6 valence electrons for group 6. 1, 2, 3, 4, 5, 6. And then we have chlorine, same group as fluorine, 7. Group 7, 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And then under neon is argon, number 8, group 8, 8 valence electrons. So again, 1, 2, 3, 4, 5, 6, 7, 8. And so on for any other elements in the same groups, 1A through 8A. Okay, so this is how you write the Lewis dot symbols. They all are based on the number of valence electrons that the element has, which are the highest energy levels. Now let's get into how we form bonds from these symbols. So again, let's remind yourself that it's the highest energy electrons. These electrons here, the valence electrons that are represented by the dots, and we're pairing up. Covalent bonds form by pairing up unpaired electrons between the atoms to make a pair. So 1 unpaired here, one unpaired here, one unpaired electron, pair them up. All right, so let's go over some examples and I'll clarify exactly what we're talking about when we're saying we're using valence bond theory or bond model to make covalent bonds and make covalent substances. Okay, let's talk about bonding now. So here we have our fluorine atoms. Notice I have two atoms of fluorine. This one has 7 valence electrons. This one has 7 valence electrons. Notice that I've written them a little bit differently. So the one unpaired electron is on this side and of this atom, and the unpaired electron of this is on this side of this atom. So again, it doesn't matter which side the unpaired electron is, as long as you have one unpaired electron and 3 paired or lone pairs. And so here, the idea is for valence bond theory or the valence bond model is that unpaired electrons are going to be coming together to form bonds, to form a pair, and that pair is shared between the two atoms and therefore creating that bond, that covalent bond. So here we have this electron is donated to the bond here. This unpaired electron is donated, they're paired up, and then you get the pair of electron that's shared between the two fluorines. And you could write it as 2 dots between them, or you could replace the 2 dots with a line representing the bond. Remember, if you have a line, it's going to have 2 electrons in that bond, right? And so the idea here is that, again, all atoms want to react in order to get a full shell, in this case, an octet. The octet rule applies. So notice that this fluorine now has an octet. So these 2 electrons here are shared between the fluorines, the two fluorines. So this pair of electrons belongs to both. So these lone pairs only belongs to this fluorine. These 3 lone pairs belong only to this fluorine, but these 2 are shared. Okay, and so you can see that now each fluorine has a full octet like the noble gas. So neon here has a full octet, as we saw, or the noble gases have a full outer shell and therefore are stable. They're not going to react very much. They're really going to form compounds with other elements. So here again, another example, we have hydrogen. Hydrogen only has 1 valence electron in the 1s orbital. So this hydrogen has 1 electron. This hydrogen has 1 valence electron. They will pair up the 2 electrons here to form a bond. These 2 electrons are now shared between the two hydrogens, forming a covalent bond, which could be represented by the line here. So either have the 2 dots of the line, and in this case, hydrogen is fine with 2 electrons. Remember that first energy level has only 2 electrons maximum. And so it's going to have the same form or same electron configuration as helium, because helium is a noble gas with only 2 electrons, and it is stable because its outer shell is full. So hydrogen is satisfied with only 2 because it mirrors or is similar to helium. It forms that helium-like structure. Now we can put fluorine and hydrogen together. So again, it's all about bonding or pairing up the unpaired electrons. So fluorine here has 1 unpaired electron, hydrogen has 1 unpaired electron. Pair them up to form a bond so that those 2 electrons can be shared. And so you have H and F with 1 pair of electrons being shared between the 2 of them, or you could write it as a line. So it's all about forming bonds or pairing up electrons in order to get stability, to get that octet, to get that full outer shell. Okay, so that's by and large the idea behind forming Lewis dot structures using valence bond model. Just pair up the unpaired electrons between the 2 atoms, so that way each atom in your molecule has a full octet, or in the case of hydrogen, has a duet. Okay. Well, what about carbon? This is where the valence bond model starts to break down a little bit. here, if we write the orbital diagram for the valence electrons of carbon, you'll see that you have 2 in the 2s that are paired up, and you have 2 unpaired electrons in the 2p. The Lewis dot symbol for carbon would look like two pair. You have this paired electrons here matching up with the 2s electrons, and then you've got the 2 unpaired electrons matching up with the 2p electrons. That's not how we wrote the Lewis dot symbol for carbon earlier. So here is the way we wrote the Lewis dot symbol. Remember, you have 4 valence electrons, so you put a dot 1 on the top, 2, 3, 4 going around. So you should have 4 unpaired electrons. That fits more with the behavior of carbon. So carbon actually exists or bonds as if it had 4 unpaired electrons. So instead of having this structure, it's as if one of the electrons here maybe went up to p orbital, the 2p orbital, so giving you 4 unpaired electrons like the symbol. And so then this allows carbon to bond 4 times and therefore create these hydrocarbons, these long chains of carbon and hydrogen. So here's an example of methane here. So if you have 4 hydrogens, each hydrogen has 1 unpaired electron, and you have carbon with 4 unpaired electrons, then carbon is going to bond with the 4 hydrogens to form 4 covalent bonds. So you see that here. So the hydrogen, the electron, the unpaired electron here will pair up with this electron, and you got 4 of these, so each of these will pair up, the unpaired electron will pair up with each of the unpaired electrons in the carbon. And so you get this structure here for methane, or you could write it with the line. So remember, you could either have the dots in between or you can have the lines in between. It's good either way. And so that's how you form the Lewis dot structures of your different compounds based on the number of unpaired electrons that you have to pair up between the atoms. Again, the Lewis dot model or the valence bond model kind of breaks down here because it doesn't quite fit with the orbital diagram that we have for carbon. There's a few other things we'll have to talk about a little bit, but let's go ahead and talk a little bit more about hydrocarbons and some other compounds that we can make Lewis dot structures from using valence bond theory, but we might have to tweak things a little bit. So stay tuned. Okay, let's talk about some hydrocarbons forming double and triple bonds. So the thing about carbon is it can form longer chains and it can form 4 bonds. So in this case, like how would we form a double bond? So let's say we have 4 hydrogens and we have 2 carbons and they're going to form a structure, they're going to form a compound. And so the 4 hydrogens with their single unpaired electron is going to pair up with each of the unpaired electrons in the carbon. We have 2 carbons this time. So the 2 carbons are going to pair up 2 unpaired electrons. So this maybe this electron is going to pair up with an unpaired electron in the other carbon. That's going to form a pair of electrons here, forming a bond between the carbons. And then each of the 4 is going to 4 hydrogens is going to pair up with the other unpaired electrons. So one hydrogen pairs up with an electron on this carbon to form a pair. This another hydrogen forms a pair with this carbon's unpaired electron, and then these 2 do the same thing with the other carbon. Now, once all that is done, you still have 2 unpaired electrons on each of the carbons. In this case, those 2 electrons can pair up between the 2 carbons to form another pair of electrons that is shared between the carbons. This creates your double bond. So there's your 2 shared pairs of electrons between the 2 carbons. And again, we can represent that as a double line for 1 line for each pair. So we have 1 pair, 2 pair. And so that is your structure. That's how you form double bonds using the valence bond model. Triple bond, same thing. You have two carbons here. The two carbons can pair up one electron each, pair up those electrons to form a bond here, a pair of electrons shaded between the carbons. These two hydrogens can pair up with one unpaired electron on each carbon. So they're going to pair up. This one's going to pair up here. This one's going to pair up here. And then you've got on both carbons two unpaired electrons. And again, the unpaired electrons on the carbon can pair up to form bonds. So in this case, we have two unpaired electrons. So that's going to form two more bonds. So we're going to form two more pairs of electrons. So here we go from this to this. And so we have three pairs of electrons being shared between the two carbons. That's your triple bond. We can represent that as lines, three lines between the two carbons. And so that's how you can form your double and triple bonds, by pairing up more unpaired electrons between the two atoms. As long as you have unpaired electrons on the two bonded atoms, you can pair those up to create more bonds, double bonds, triple bonds. Now, what about nitrogen? Nitrogen here, we have nitrogen. If you look at the orbital diagram for nitrogen, it has two pairs of electrons. It has a pair of electrons in the 2s and three unpaired electrons, and that matches with the Lewis dot symbol that we drew before. So then in this case, if we have three hydrogens, each of the hydrogen with its unpaired electron can pair up with the unpaired electron on the nitrogen. We have three unpaired electrons here. We have three hydrogens, so that those hydrogens can pair up the unpaired electrons to form covalent bonds, and then we're left with this lone pair on the nitrogen. And so then we can represent this as three lines and one pair of lone pairs on the nitrogen. So that's how you would write the Lewis dot structure for NH3, for ammonia. Okay. But what about other nitrogen products? Let's continue and look at other examples. Okay, let's quickly go over these. So here in this case, you have ammonium, which is NH4 plus. And so in this case, ammonia would, or the nitrogen would need to bond 4 times, but we only have 3 unpaired electrons here. So it's as if nitrogen here is losing an electron. So it loses an electron from the pair, and then therefore now you have 4 unpaired electrons with a plus charge on the nitrogen. So now you can take 4 hydrogens with their unpaired electrons, pair those up with each of the unpaired electrons here with a plus charge, and now you get the 4 bonded hydrogens to your ammonium with a plus charge. So it's as if nitrogen lost an electron in order to form that Lewis dot structure. For oxygen, we have oxygen here. Oxygen has 2 lone pairs, so it's got 6 valence electrons, 2 lone pairs, unpaired electrons. So here's the Lewis dot structure, it's Lewis dot symbol for oxygen. So when you form for oxygen with hydrogen, you have 2 unpaired electrons. You have the hydrogen here with unpaired electrons. 2 of them, each of them will pair up with each of these 2 unpaired electrons, and we're going to form water with 2 hydrogens sharing the electron pairs between them, and then oxygen has 2 lone pairs. And so here's the other way to write this with the lines. Okay, now what about something like OH minus, right? So OH minus here, it looks as if oxygen here gained an electron, right? So it forms 1 bond. So to form that 1 bond, you would need 1 unpaired electron. So it gains an electron here, and then you add that to the orbital diagram. You have 1 unpaired electron, and so now you have 1 unpaired electron in the Lewis dot symbol, so instead of 2. And so now you can pair up 1 hydrogen with that 1 unpaired electron to form OH minus. And so that's what you get here. So you can use the valence bond model to kind of explain these as well. So that's it for this video. Thanks for joining me, and see you next time.